Alright, so this video is about the basic computational issues that we have in game theory. Okay, now game theory helps us analyze strategic interactions between players, right? But when we try to solve these games using computers, we face several difficulties. Okay, now as games get bigger or more realistic, they become harder to compute, okay, or handle. Now, specifically, first of all, it's very hard to calculate a Nash equilibrium. The Nash equilibrium tells us the best strategy for all players, right? But finding even one Nash equilibrium can be very slow for computers. As long as we have emphasis on Nash equilibrium in game theory, finding even one is pretty hard. We've been doing it in very minimal matrices, right? But actually finding it in a real game scenario is very hard for a computer as well. So as the number of players or strategies increases, the calculation becomes too complex. Okay. Now what is it called? It's called a PPAD complete problem. Means no fast method exists for all games. Okay. Then we have exponential growth. A strategy space grows too fast. Okay. So more players will mean more possible outcomes. For example, if we have two players and 10 strategies, that will mean 100 outcomes. But if we have two players and 100 strategies, that will mean 10,000 outcomes. This rapid growth is called combinatorial explosion. Okay, then there is difficulty in representing large games. Payoff matrices or game trees will become too large to store memory. Okay, so what happens in multiplayer games especially require huge storage space and complex representations. So we need smarter ways to store games. For example, graphical models is one example, which is kind of a smarter way to do this. Then we have to choose the right equilibrium. Okay, then many games have multiple equilibria, right? So which one should be used? That question arises. Then most computers must check which is stable, which is reasonable, which avoids unrealistic threats. And this makes it very hard to find a proper singular equilibrium. Then we have computational strategies with mixed computational complexes with com- computational problems with mixed strategies. Okay, now what do these do? Players randomize strategies by using probabilities, right, in mixed strategies. Now, to compute this, these computers must solve non-linear equations. And as the players and the strategies increase, this becomes very, very slow. Then perfect and imperfect or incomplete information in games like auctions and signaling where it is used, players don't know everything, right? Now a computer must model beliefs and update them using probabilities. This adds extra layers of complexity. Then we have iterative algorithms, which may not converge. So iterative methods like best response or fictitious play, they update strategies repeatedly. In this case, problems will take too long and even might never reach an equilibrium. So computers struggle in large and messy games. Okay. Then we have computation of cooperative solutions. Cooperative solutions like Shapley value require checking every possible collision. So what happens in coalitions is that they grow exponentially with the number of players. Now you see where this is going. If we have 10 players, then we are going to have 1024. Just an example, okay, 1024 coalitions. And it's very hard for computers to compute this efficiently. Then there's the approximation of heuristic methods. Okay, they aren't perfect because exact solutions are hard. We use heuristics, evolutionary methods, and reinforcement learning, but they might not reach to equilibrium and can be inaccurate also. Real time decision making is also difficult. Now, what happens in real applications like online advertising, traffic routing? Computers must decide instantly. Now, large game computation can cause slow responses, which can make systems less effective. Now, this problem is probably going to come for 5 marks. So you write at max any five of these points, all right, or maybe even four if you add the definition. Actually, write five disadvantages, whether or not you write an intro to the answer. But yeah, this question was asked. So yeah, these are the computational problems in game theory. Thank you for watching the video.